There was a question about hydraulic jump, and hydraulic jump is a phenomenon that many of us probably have seen. It's super easy to generate it at home. All you need is a running water, like a faucet or something, and a flat surface. That can be a sink or a saucepan or anything. So I'm here opening the faucet to a saucepan. As you can see, there is this water basically moving away from the center, and there's a jump here, as you can see. Let's just wait, maybe right there. So water moves away from the stream radially, and then all of a sudden there's this little jump here, right, from this height to a new height, right? So this is called a hydraulic jump, and as I said, this can be seen in many different scenarios or many different places. Let's understand what it is physically, and then we try to see what we can do with the knowledge of fluid mechanics to even better understand the details of that. Let's get rid of this. All right. So let me consider a flat surface. And then in one dimension, now what we saw is a radial version of hydraulic jump, but this also happens in one dimension. So in one dimension, what we have is we have a stream with a velocity v, right? And then all of a sudden, at some point, it becomes just complicated, right? A lot of turbulence and vortices and all kind of things. And then a little up and downs, and then eventually far away from the location of the hydraulic jump. And I can just call this is the area of the hydraulic jump. The far away from that area, then again, we're going to have a pretty uniform stream of flow. Now, if velocity here is v1, and then the area is a1, and velocity here, on average v2, we assume the velocity is uniform, and the area is a2, then a1 v1, conservation of mass, is equal to a2 v2, of course, right? It has to be the case. In fact, a1 v times a has to be constant pretty much every year. But what happens that results in a jump? Well, that has to do with the momentum balance and friction and everything. And let me try to explain this in a very qualitative way. So let's assume this is the surface, rigid surface. It's not moving, but there's of course friction. All right. And then let's assume that we have a flow on top of this. So clearly there is friction here, right? So the friction, shear stress, is trying to stop the flow. And it does that. So what happens is that slowly the velocity decreases and further decreases and further decreases. And at some point the velocity becomes zero, right? Now, because a times v has to be constant, if velocity decreases, the area has to increase. And guess what the area is at this point? Well, the velocity is zero, so the cross-sectional area has to go to infinity, right? So it has to be something like this. But well, can that happen? Can we have water piling up? Of course not, because we have gravity and perturbation and everything. So water is going to basically fall down from one way and also the other way, right? And then that's how we're going to have some vortices basically being generated. Now, what happens next is also interesting. But let me give you an analogy, and hopefully that's going to help you better really understand the concept behind hydraulic jump. So let's assume we have a little car, all right, on a road. And let me draw a road here. So this is the road, and this is our little car. Maybe I can make it a little aerodynamic car. There you go. That's not bad. All right. So let's assume that at a given point here, okay, all cars, there's a stream of cars, like a fluid flow. Cars going to turn off their engines, right? And then they let them just come to a stop because of friction. So what happens is that at this point, all cars have a velocity of v. This one, which is our first car, is going to just turn off the engine on neutral, and what's going to happen is that it's going to come to a stop at a given point, right? let me draw a line here, because this is where all cars going to come to stop if they let's see what I can do here. Nope, that's okay. Let me try one more time. So I just want to draw a vertical line here, and this is easy. All right, so this car is going to come to a stop at that location. Now, what happens to the next car? So if there is another car here, that car wants to also come to this location and come to a stop. But of course, there's this car in front of it, so it's going to basically hit this car. It's going to hit this car, and as a result, there's going to be a little damage. But then both cars are going to move a little further forward, right? Then we're going to have a third car, and this one wants to come again to come to a stop here, but there's a car further upstream. So it's going to hit this car even faster, even stronger. So it's going to hit this car even stronger. And then all three are going to move a little further down, right? The next one, the same story. And now, because now this end, oops, sorry, I can keep the color, because this end is now even closer to the location that the car has the maximum momentum v0, the impact is going to be even stronger. So potentially this car even can go a little bit on top of the other cars, right? And then everything is going to move forward a little further, right? And then this is going to just continue. And then if you just basically follow or just keep on drawing, you're going to see that we're going to have pile up of cars right here, here, here. And then somehow at t infinity, this is what we're going to have, right? Now, at a very large time, right, we're going to have these cars damaged because of the impact piled up, right? So what we see on this side, if you look at this at t infinity, is this kind of thing. There's a stream of car coming in, and then there's a pileup of the cars, right? And then because every incoming car is going to hit the pileup, what's going to happen is that the pileup is going to move with a new velocity. Yep, so it's going to move with the velocity v, lowercase v, which is different than the velocity capital V, which is at the beginning. And this is exactly the hydraulic jump that we talked about. So what happens is that because of friction, one car comes to a stop, and then the other car is going to hit the first car, and then there's going to be a lot of turbulence, but eventually the pile of cars, right, that is being generated at this point. And again, this point is not the point at which velocity naturally reaches zero, right? It's a little behind that. The pile of the cars is going to move forward with a given velocity, which is the lowercase v. So this is physically basically what happens. So as I said here, we're going to have these water coming down, and then lots of vortices and lots of perturbations and chaos here. But then eventually what's going to happen, we have a pile of molecules that are being pushed forward because of the momentum that is brought in by the incident stream with a new velocity. And this new velocity, is, of course, has to be less than the velocity of the input because of conservation of mass. And later on, we're going to show that momentum is going to basically help us to better even understand how things work out here. So that's the physical concept and idea behind hydraulic jump. Now, here, our analogy, we talk about gravity that causes the hydraulic jump. It can be the surface tension, right? So we just said that the gravity, the water is going to pile up, and gravity is going to pull this down, right? It can be also surface tensions, because if the curvature is too high as a surface tension, then it's going to come into play, or other factors. All right, so then what we're going to do, we're going to use dimensional analysis and control volume analysis to better understand basically how hydraulic jump works.